rates. So in chemical reactions, some reactions are going to go really fast and some reactions are going to go really slow. Some reactions might go some kind of middle ground. Okay, so in this case, obviously, this is a very fast reaction. An example of a fast reaction would be like a firecracker. An example of a slow reaction would be something like how dead plants decompose to make coal. And something that would be moderate would be something like your food spoiling after you've cooked a nice meal and you put all your leftovers in the refrigerator. They go into the very back of the refrigerator, and then all of a sudden you realize, oh my gosh, those leftovers have gone bad after a week. So we might want to speed up a reaction to make the product faster, or slow down a reaction to have the effect last longer. In chemistry, we're going to express reaction rate as the amount of reactant change per unit time. An example of that would be like 3 moles per year or 5 grams per second. So what collision theory is it's talking about how particles need to collide in order for a reaction to take place. The main idea is that the reaction must take place by the molecules touching or colliding. But what happens is when they collide, they have to have a couple of components. First, the particles have to have sufficient amount of energy, so enough energy. And they also have to have proper orientation. So an example that I would use for proper orientation is if you're trying to put a cap on a pen. When you're trying to put a cap on a pen, you have to put that cap going a specific direction on top of that pen, or else the cap is not going to fit on top of the pen. So that's the correct orientation for that to happen. Okay. If you don't provide enough energy to put that cap on, the cap is going to end up falling off. So if we look at this right here, this is the process by which a reaction ends up taking place. Now you'll see that hill right there. That hill is your activation energy. It's the amount of energy required for a reaction to take place. Now, as you see your reactants, starting at the very beginning on that left-hand side, they move up, all the way up to the activated complex. And at the activated complex, that's the transition state. It's a very unstable arrangement of atoms that forms momentarily at the peak of the activation energy. It's very unstable. If the reaction has enough energy to push over that activated complex and to break into the products, then the reaction will go to the end. If the reaction does not have enough energy to go up over that activation energy, then the reactants will come back down and will remain as reactants. But that activated complex is a very unstable point of transition where the bonds have almost like the bonds have been formed, but other bonds haven't been broken yet. Is this reaction producing heat? Think about this way. Right here, we have energy. So we have energy here the energy is higher here and lower here. Is energy being produced or is energy being absorbed? What I mean is energy being released or is energy being absorbed? When we look at this diagram right here, this is actually how we diagram our chemical reactions. So if you look over on the right-hand side, we have our reactants, and then our reactants move up into our activation energy. Every single reaction has an activation energy. It's just a matter of what type of reaction is it? Is the activation energy high? Is it low? When we are looking at if it's an endothermic versus an exothermic reaction, we're looking at the energy of the reactants versus the energy of the products. So if the energy of the reactants is higher than the energy of the products, then this would be an exothermic reaction because energy is exiting or being released. If the energy of the products is higher than the energy of the reactants, then that would be an endothermic reaction, or overall energy is entering in order for the reaction to take place. Right here on the y-axis, we have energy, and then the x-axis, progress of the reaction. So this would be as you go from left to right, that's the forward reaction. As you go from right to left, that's the reverse reaction. Now in this case, we have our exothermic reaction. And if I wanted to find the delta H, or the enthalpy of the reaction, or the heat of the reaction, it's the heat of the products minus the heat of the reactants. So notice I have the reactants are at 100 and the products are at 50. So products minus reactants. I have 50 minus 100. I have a release, or negative 50 joules. I have a release of 50 joules. This is an exothermic reaction. Now, in this case, what do you think? Is this endothermic or exothermic? Well, let's look at it. We have the heat of the products minus the heat of the reactants. We have 300 minus 100, and that's going to end up giving us a heat of reaction of 200 joules. In this case, because our energy is positive, this is an endothermic reaction. Now, there are some factors that are going to affect a reaction rate, okay? One of those factors that's going to affect a reaction rate is increasing the temperature. Increasing the temperature is always going to increase the rate of the reaction. And the reason for that is because when I increase the temperature, I'm increasing the particle collisions. I'm increasing the speed of the particle collisions. And so I'm increasing the energy. This allows the collisions to have sufficient energy for a reaction to take place. So increasing the temperature increases the speed of the particles, which means that the collisions are going to have a high enough energy. Another situation that's going to increase the rate of the reaction is if I increase the surface area. And in order to increase the surface area, I would crush something up. So by crushing something, I am going to, or breaking it up into pieces, I'm going to increase the rate of the reaction. And I'm going to do this because increasing the amount of sites that are available for collision increases the likelihood of me having the favorable orientation. Another situation that's usually going to increase the rate of a reaction is if I increase the concentration, because the particles that are there, the particles pack together more closely, so the collision can occur more often. Okay, so if I have more concentration or higher concentration, I have my particles closer together, and so they're going to be able to collide more often. Now, when I'm looking at this diagram, so this is the diagram you saw before, but you see this red line right here. This is our regular reaction, okay, the regular graph of our reaction. But if I add a catalyst, what a catalyst does is a catalyst speeds up the rate of the reaction by lowering the activation energy. I haven't changed the energy of the reactants or the products. I haven't changed what the reactants or the products are. What I've done is I've added a substance, or I've added something, a catalyst, so that I can change the path that the reaction needs to take place. So for example, anyone who's a runner can kind of relate to this, but say I had a path that I'm going to follow and I'm running on my trail, and the trail that is originally there has a really high hill. But maybe one day people don't want to run the hill and they kind of want to run a shorter part of the hill, maybe around the hill or just a smaller hill. So they start a new path. That starting a new path, I'm still starting at my beginning and ending at my end, but I've changed the energy required. My hill isn't as steep. I've changed the energy required in order for the reaction to take place. By lowering the activation energy, I'm going to speed up the rate of the reaction. Now, you have actually have experience with catalysts in your body. You have catalysts within your body. Those are called enzymes. Enzymes speed up the rate of the chemical reaction within your body. Now, when I have a reaction that I don't want to speed up, that I want to slow down the reaction, I can give the reaction an inhibitor. So an inhibitor will actually interfere with the action of a catalyst. It will inhibit or slow down the rate of the reaction and maybe even stop the chemical reaction. So one last thing that I wanted to talk to you about is stoichiometry and reaction rate. So if I'm looking at Na2SO4, and this should be an arrow, Na2SO4 produces 2 Na++ SO4 2-. If the rate of the reaction, the rate at which Na2SO4 is consumed, is 0.250 molar per second, then I can use stoichiometry to see, okay, so 0.25 here, so then that's going to be 0.5 here. So Na plus is produced at a rate of 0.5, and SO4 2 minus is produced at a rate of 0.250 because I have a 1-to-1 ratio for my Na2SO4 and my SO4 2 minus, and I have a 1-to-2 ratio for my Na2SO4 to 2 Na plus. Hopefully that was helpful for you. If you have any questions, please don't hesitate to reach out.